Hello everyone, and welcome back to another calculus video. In this video, we are going to talk about alternating series. So when I say alternating series, I want you to think about a series that is going to bounce back and forth between positive numbers and negative numbers. And there's lots of different ways that we could write this. We could have the sum from n equals 1 to infinity of negative 1 to the n plus 1 times some sequence b sub n. So when I plug in 1, then that exponent on that negative 1 is going to be a 2, which means I'm going to start with a positive. But then when I plug in 2, I'm going to have a 2 plus 1, which is 3, on that negative 1, which is a negative. And we're just going to kind of keep bouncing back and forth between positive, negative, positive, negative. We could also write it as the sum from n equals 1 to infinity of negative 1 to the n times some sequence b sub n. So here, when I plug in 1, I'm going to have negative 1 to the first power, which is negative. And that next term, I'm going to have negative 1 to the second power, which is positive. And we're going to bounce back and forth, negative, positive, negative, positive. So in either way, I'm going to end up with this alternating series where I'm bouncing back and forth between positive numbers and negative numbers. So there's a test for alternating series. An alternating series that's in one of those forms is going to converge if two criteria are met. The first criteria says that 0 has to be less than b sub n plus 1, which is less than or equal to b sub n, which means that the next term has to be smaller than or equal to the previous term. So I've got something that's decreasing here. And that's going to happen at some point in the sequence. Everything ends up decreasing. Okay, it does not have to happen initially. The first term or two or three, there could be a finite number of terms in the beginning where it's not decreasing, but then at some point, everything past that point decreases, is what that's trying to say. And then the second condition is the limit, as n goes to infinity of b sub n, has to go to 0. If those two criteria are met, then we have a series, alternating series that is going to converge. So let's look at a few examples. The first one, we're looking at the sum from n equals 1 to infinity of negative 1 to the n plus 1 over n squared. So this is an alternating p series. So let's look at our two criteria. Okay, the first one says that b sub n plus 1 has to be less than or equal to b sub n. We need to know if that's going to be true. Now, when we talk about b sub n, we are talking about the non-alternating part. So in this case, I'm looking at 1 over n squared. And then I'm going to look at comparing that to 1 over n plus 1 quantity squared. And this is definitely going to be a decreasing series. 1 over n squared has a smaller denominator, so that fraction is going to be larger than 1 over n plus 1 quantity squared. So the first criteria is met. The second one is looking at the limit as n goes to infinity of the sequence, which is 1 over n squared, and we can see that guy's heading to 0. So we would say, therefore, this series converges by alternating series test. I'm going to abbreviate that AST. Let's look at B. We're looking at the sum from n equals 1 to infinity of negative 1 to the n plus 1 times n over n plus 1. So my b sub n here, label this part B, is n over n plus 1. It's alternating because I've got that negative 1 to the n plus 1. So the first term is going to be positive, the second term is going to be negative, and it's just going to bounce back and forth between positives and negatives. Two criteria we have to check. Is b sub n plus 1 less than or equal to b sub n? So we're going to have n plus 1 over n plus 1 quantity squared. We want to know if that's less than or equal to n over n plus 1. Oops, I'm not sure. Let me try that again. So b sub n is n over n plus 1. When I plug in n plus 1, I get n plus 1 over n plus 1 plus 1. So that's going to be n plus 1 over n plus 2. So I'm just going to set up an Excel spreadsheet. So I've got a column for n. This is n over n plus 1, and this is the n plus 1 over n plus 2, which is what we had here. I want to know, is n plus 1 over n plus 2 less than n over n plus 1? So is this the smaller column? So I'm starting with 1, 2, and then I'm just going to add 1. This is going to be equal to n divided by n plus 1. And this is going to be equal to parentheses n plus 1 divided by n plus 2. As you can see, when we plugged in that n plus 1, to me it looks like it's always bigger than the other column, just by a little bit. Let's see. Yeah, it's always slightly bigger. So that first criteria is not even met. So I'm just going to put an X here. That fails. And check out what happens if we try to take that limit. If we take the limit as n goes to infinity of that sequence, n over n plus 1, we would have to apply L'Hopital's. So we would say the limit as n goes to infinity, take derivative of the top and the derivative of the bottom, and notice that limit's going to 1. And since that's not 0, what this means is that the alternating series test is inconclusive. So we can't use it for this because the criteria is not met, which means we've got to try something different. That criteria is not met. Okay, but what we do know is that the limit of that sequence went to 1, which is not 0, so we could use the divergence test. And the conclusion here is that the sequence diverges. So we've got an example where the alternating series test works and it's applicable, and another one where the alternating series test does not apply. That does not mean that it's divergent. That means we have to try a different test when that happens. So now let's look at absolute and conditional convergence. A series, the sum of n equals 1 to infinity of a sub n, exhibits absolute convergence if the sum from n equals 1 to infinity of the absolute value of a sub n converges. That same series is going to exhibit conditional convergence if the sum from n equals 1 to infinity of a sub n converges, but the absolute value diverges. Now, if we have a sum from n equals 1 to infinity of the absolute value of a sub n, okay, notice that that's the positive series. If that positive series converges, then that means that the regular series, whatever it is going to converge also. So we're really trying to figure out what kind of conditions will this converge? Does it converge always, even with the alternating piece, or does it converge without the alternating piece as well? Just looking at positive values. And that's what that absolute value is doing for us. So let's look at example 3. In part A, we're looking at the sum from n equals 1 to infinity of negative 1 to the n plus 1 over 3n plus 1. We want to know if it converges absolutely, conditionally, or diverges. So let's start with the absolute value. So I'm going to look at the sum from n equals 1 to infinity of the absolute value of the series. And that's going to be the sum from n equals 1 to infinity of 1 over 3n plus 1. So let's do a limit comparison test. It looks really similar to a harmonic series, which we know diverges. And the limit then goes to infinity. I've got that 1 over 3n plus 1, and I'm dividing it by 1 over n. We're going to do keep, change, flip. So now looking at the limit as n goes to infinity of n over 3n plus 1, and that is infinity over infinity, which means use L'Hopital's. So I'm going to get 1 over 3, and that is 1/3. So if you remember, the limit comparison test said that if you take the limit of the ratio of the sequences, okay, what you're comparing it to and what you started with, and you get some number that is not 0, and 1/3 is definitely not the same thing as 0, then that means both series either converge or diverge. So that sum from n equals 1 to infinity of 1 over 3n plus 1 must do the same thing as the harmonic series, which means it has to diverge. So now let's look at the sum from n equals 1 to infinity of the alternating series. Remember, two criteria have to be met. The first one is a sub n plus 1 has to be less than or equal to a sub n. So my a sub n is 1 over 3n plus 1. I've got 1 over 3 times n plus 1 plus 1. I want to know, is that less than or equal to 1 over 3n plus 1? So this is going to be 1 over 3n plus 4 when I distribute and combine the bottom. And since that denominator is larger, the fraction is smaller, so that condition is met. The second one says that the limit of the sequence, which is 1 over 3n plus 1, has to go to 0, and it does. So we can say, therefore, this converges by the alternating series test. So our conclusion, the positive diverged, but the alternating series converged. So this sequence, the sum from n equals 1 to infinity of negative 1 to the n plus 1 over 3n plus 1, converges conditionally. So let's look at that next one, the sum from n equals 1 to infinity of cosine of n over n squared. So we're going to I'm going to start with the absolute value one again. Negative 1 to infinity. So I'm going to look at the absolute value of cosine of n over n squared. And notice as n gets bigger and bigger, this is going to have some negative terms in it. It's not really an alternating series. Let me pull up Excel again. So we're looking at cosine of n divided by n squared. It's really alternating because it's not positive, negative, positive, negative, or negative, positive, negative, positive. But we are going to have positive terms and negative terms. It's just not in that very predictable pattern. So we're going to have cosine of n, which is an a1, divided by n, which is an a1 squared. So cosine of 1 is going to be a positive number. And then we're going to, and then we have a few negative numbers. And then we're back to positive. So you see it's bouncing, but it's not every other term. And that's the definition of an alternating series, is every other term. So the every other term thing is not happening. So let's look at what happens with that positive. Now, n squared is always going to be positive. So I'm really comparing and looking at what happens when that cosine is always positive over n squared. So let's see if we can figure out what we can compare this to. Maybe we can compare it to 1 over n squared, which we know is a convergent p-series. So let's try a direct comparison. So the direct comparison test says that if a sub n is less than or equal to b sub n, and all the terms are bigger than 0, which I'm not going to write, then if the sum from n equals 1 to infinity of b sub n converges, and we picked our b sub n, then the sum from n equals 1 to infinity of a sub n has to converge also. So the question is, if my b sub n is 1 over n squared, is the original sequence, which is absolute value cosine of n over n squared, is that less than? So are my b values bigger than my a values? So we're going to use Excel to help figure that out again. I'm going to go back to Excel. And I'm going to look at absolute value. Oops. I'm typing ABS for absolute value. So absolute value of the cosine of n divided by n squared. I don't know why it's giving me an issue. Equals absolute value of cosine of 1 divided by n squared. So that's going to return positive numbers. I want to know if this is less than what I picked, which was 1 over n squared. Equals 1 divided by n squared. And you can see how these are definitely smaller than what I picked. So our criteria has been met. Which means that this, therefore, converges. So the sum from n equals 1 to infinity of the absolute value of cosine of n over n squared converges. by direct comparison test. And I'll abbreviate that DCT. So now let's look at the original sequence. Actually, we don't even have to look at the original sequence because since we know that the positive is always going to converge, then our theorem up here said that the original sequence has to converge also. So by theorem 515, theorem 515, the sum from n equals 1 to infinity, cosine of n over n squared converges. So we would say this sequence converges